Start.
Good evening, dear members. Thank you very much for joining this webinar series. This is organizing by the Young Members section of the Institution of Engineers Sri Lanka. I'm so proud to start this Young Members section talk series. This will be the first session that we are arranging for this session 2024-2025. And our theme is Engineering Evolution and Road to 2015. So we will be taking various topics and multidisciplinary areas to be discussed. And we will be covering all of engineering disciplines, which will be impacting to the development of the nation. And I'm so proud to introduce our moderator today, Engineer Samitha Karunaratne, the electrical engineer of the Sri Lankan Electricity Board, and the chief organizer of the Young Members section for the session 2024-2025. And he's an active member at ISL activities. And today our speaker is very known person, Engineer Amila. I hope you are doing well, Amila. Today I'm at the university.
Yeah, I see that. It's ISL day, right?
Yeah, yes. I think the background is familiar to you. I'm at the university. And we had a very fruitful session at ISL Day 2025. And we remembered your contribution for the ISL chapter as well. And it's good to see you. You are doing well. And without taking much time, I would like to hand over the control to Engineer Samitha Karunaratne, the moderator and the chief organizer of Young Members section. Engineer Samitha, over to you.
Thank you, Mr. Chairman, Engineer Dushanta Vanyarachi. Ladies and gentlemen, please welcome Engineer Amila Premakumara. He is a dedicated researcher and engineer specializing in clean energy systems with strong focus on hydrogen technologies, energy security, and sustainable infrastructure. Currently pursuing his PhD at the University of Melbourne, his research delves into scaling of liquid hydrogen storage to mega-scale applications. He joined the University of Melbourne, earning his prestigious Melbourne Research Scholarship in 2023, subsequent to obtaining a first-class honours degree in civil engineering from University of Moratuwa in 2022. His work is at the forefront of hydrogen innovation, particularly in cryogenic engineering, where he investigates the properties of materials at liquid hydrogen's extreme operating temperature of minus 253 degrees Celsius. This involves evaluating mechanical and connection strengths of metal and composite materials, as well as optimizing cryogenic insulation to enhance efficiency and safety in hydrogen storage and transport. Beyond his technical research, he is deeply engaged in analyzing the global hydrogen landscape and its evolving supply chain. His expertise spans both the technical and policy dimensions of energy transitions, including the decarbonization of power generation, industrial processes, building, heating, recovery, resource recovery, and transport sectors, positioning hydrogen as a critical enabler in achieving net zero targets. With a strong passion for Sri Lanka's energy future, he brings valuable insights into how hydrogen can harness as a clean energy carrier to support the country's sustainability ambitions. His work critically assesses the feasibility, adaptation, and integration of hydrogen technologies within Sri Lanka's energy ecosystem, comparing policy frameworks, financial feasibility, and technical capabilities against global best practices. So, Engineer Amila Premakumara, we welcome you to the first episode of Engineering Evolution, the Road to 2050. So before we go deeper, could you briefly introduce your involvement in hydrogen and energy research?
Yeah, thank you very much, first of all, for that wonderful introduction. It's really nice of you. And Engineer Dushanta, thank you very much for the being here for Mr. busy schedule. I'm sure that the ISL day must have been a really good one at Moratuwa. That's where I started as well. Answering to your question, Samitha, right now, what we are doing at the moment at University of Melbourne in my PhD, what we are trying to do is we are trying to come up with a storage tank that is, we are talking about the mega scale. Mega means 10 to the power 6. That scale of storage tanks for liquid hydrogen. So usually there are storage tanks that's already around 1,000 to 5,000 cubic meters that is already available. But the scaling up is really crucial because if we are to enable hydrogen as the next generation fuel, obviously we need these large scale storages or mega scale storages. So in this particular phenomenon, what I am and our team doing at the Melbourne is trying to improve this scale up the storage and improve its structural feasibility or the capacity, and the insulation properties that could withstand, as you mentioned, the minus 253 Celsius storage temperature, because it's not easy. So because usually if you have a hot drink in your hand, what happens is heat goes out. But in this case, heat comes in. You need to prevent the heat coming in. So we are storing the liquid at minus 253, and preventing that heat coming in is not easy. So that's where we are working on at the moment. And I need to acknowledge my team. I will be doing it at the end of session because everything we do right now in here, as we all know, it's a team work. So we have our own individual component, but at the same time, the ultimate goal comes as a team's effort. So that's basically what we're trying to do at Melbourne.
Okay, great. So we will move to the next question. So as the world moves towards cleaner energy, solar and wind have been widely adopted. So while battery storage offers short-term solutions, hydrogen is gaining traction as a long-term energy carrier. So what makes hydrogen a standout solution compared to the other renewable storage technologies? And how do you see its role evolving in the global energy transition?
Yeah, that's the ultimate question. Thank you very much. So to be honest, now we all know what we have heard about hydrogen, but sometimes for the audience or anyone who's listening in for the first time, the hydrogen could be something like a new topic. So basically what we know about hydrogen is something like it's the first element in the periodic table. But in this sense, when we are talking about energy, what we consider hydrogen is as to be an energy carrier. So basically like a battery. So the question is why we needed hydrogen. So that's where we need to start the conversation. So the reason is because we are burning off a lot of fossil fuels again and again and again. Now the world have pledged to reduce the global warming by keeping the temperature rise less than 1.5 Celsius. That's the Paris Agreement. But unfortunately, we are not running into the expected standards. But anyway, and again, we are trying to reduce the global greenhouse gas emissions by 45% compared to 2005 levels, which is because it is really has gone a lot than the 2005 levels now, but still we are trying to reduce it by 45% of 2005 levels. Still, we are not there. So what has happened is the renewable energy has come forth, the solar has come forth, wind has come forth, and the tidal wave, geothermal, a lot of alternatives have come forth. But the problem is all these energy sources, they are intermittent. That means that they don't have a steady operation. So let's say you have solar in the daytime, it is not steady. So if you start from 9 a.m. to 5 p.m., the solar irradiation you get is not steady. And at the same time, the solar that you get today, it won't be available tomorrow. So what happens is this input is not steady. So we cannot have anything operational that is, how to say, like in a particular manner that is steadfast. We can't do it. So that is where we need to improve how to store this renewable energy. So how can we do that? So basically for this option, the world has come up with three effective solutions. One is obviously hydrogen, and the battery energy storage and pumped hydro. So that is the basic three components that the world have looked at it. But the problem with pumped hydro is it's really effective. But the thing is we cannot build pumped hydro everywhere because you need to have a large water source and you need to pump it up and again run turbines and likewise. It's not easy. And at the same time, battery energy storage, the happen is you need rare earth metals, and using it in large scale, it's not again feasible because you need lot of earth metals, which is not easy or convenient. So that's why hydrogen has come forth, because if you make hydrogen from electrolysis, so we call it as green hydrogen. So what happens is you do not emit anything, like you emit water, obviously, but any harmful emissions. So that means it's really green. So Samit, I think you can see my screen. So I will just showcase a little bit about this hydrogen economy, what happens.
Yeah, we can see.
Yeah, so this is a nice figure that we have derived from the one of our manuscript. I need to acknowledge the authors I have mentioned below. So you can see the hydrogen supply chain, which is in green. So you can see this, the renewable plants. If we use solar, hydro, and wind, and if we can use these electrolysis of autobiocatalyst or thermochemical cycles, the hydrogen that we generate, produce, it's green. So in this process, you do not emit anything harmful. So if you can produce hydrogen in this way, and if you can store it and then use it laterwards, so that means that you are emitting, like you are reducing the harmful emissions by fossil fuels completely. So this is why hydrogen has gained momentum all throughout the years. So that is what people are trying to come up with as well. And again, if I just compare the liquid form of hydrogen to petrol, so the energy in 1 kilogram is almost like 3 times. That's far superior in the same time. And of course, there are some safety concerns. We can talk about this later. But altogether, hydrogen, once you consider it in a denser form, like in liquid, the density is high as well, and it's have a high octane number, more than 130. So, you know, with the petrol that we use is around 95, 98. So 130 plus octane number is there as well. And the flammable range is around 4% to 75%, large flammable range is there. So that enabled hydrogen to be used as a good end-use applications as well. But mostly we can produce this without any harmful emissions. And once you use it at the end use or the end level at the supply chain, we do not have any harmful emissions again. So that's the basic principle behind hydrogen and why it is getting a lot of momentum around the world. I think
Yeah.
directly on the question.
Thank you for that comprehensive answer. So I will go to the next question. Decarbonization of the power sector is crucial for achieving net zero targets. Hydrogen, especially green hydrogen, is better considered as a clean fuel. So, which sectors will experience the greatest impact from hydrogen adaptation? Where in this question, I also expect what is the difference of this green hydrogen compared to other kind of hydrogen we have at the moment?
Yeah, that's really important because these technical terms. So basically, so I can explain from this chart. Again, this is something that is from a review that we have done in Melbourne regarding this global hydrogen supply chain. So basically, you know, hydrogen is we can found it in a gas form in our Earth, right? So in gas form, so if you can use the gas itself, you know, it's very light. So it basically goes up. If you can fill it into a balloon or something, it just goes up because it's very light. So that means the density is pretty less. So in order to use this hydrogen in any way, we need to compress it. Compress it like you are compressing it, you're having a high pressure. So usually we have 100 bar compressed gas storages. We have 200 and 700 bar storages, that is cryocompressed storages. And we have liquid hydrogen. So that means that you pressurize it again and you make it a liquid by cooling down as well. So these are the pure hydrogen forms. And at the same time, we have material-based hydrogen. So that is chemical hydrides, metal hydrides, and liquid organic hydrogen carriers. So then I can go back to this slide and explain. So what happens is hydrogen, if it is available within our atmosphere or our ecosystem, or if you can like mine it, we call it white hydrogen. That is not readily available around the world. So we have to produce it almost all the time. So if you use a greener method, so greener method means that you are not emitting any pollutant to the atmosphere, that is green hydrogen. So if you can see this chart, if you use solar, hydro, and wind energy itself, that means that you are not giving any pollutants to the world. And at the same time, if you use that energy to drive electrolysis and generate hydrogen, that means that it is green. So, and if you can see this nuclear one in here, this is called pink hydrogen. That means that you are using the electricity from nuclear power plants to run to generate hydrogen. So that means it is called pink hydrogen. And if you use coal, natural gas like LNG or fossil fuels to generate hydrogen, that means it is from their techniques called pyrolysis and steam methane reformation, regasification. This is we call basically gray hydrogen or blue hydrogen. So right now, 99% of hydrogen production in the world is either gray or blue. it's like 1% of hydrogen of the global demand is manufactured by green hydrogen right now as well. So that's why we are trying to promote this green hydrogen perspective. So that's what we are trying to do here as well. So basically, gray blue means basically we are emitting the same as we use coal, natural gas, and everything. Green is the most sustainable solution, and in the meantime, pink is debatable whether we should go with nuclear or not. That's a debatable question because some economies are trying to use pink hydrogen, that is mostly the USA. And up until now, the Australia is more focused on green hydrogen, and likewise, different countries had different perspective. So we need to see in the front what would be the best option.
Okay, interesting. Thank you for that comprehensive answer again. So meanwhile, we are proceeding with the questions. I request our valuable listeners to type their questions in the textbook. So we can answer those questions at the end of the session. So Engineer Amira, then I will go to my next question. So we heard that major economies are heavily investing in hydrogen, with some countries establishing large-scale hydrogen production hubs and cross-border hydrogen trade agreements. So which nations are making the most progress, and what strategies are they implementing to scale up the hydrogen supply chain at the moment?
Yeah, that's really important as well because right now I would say so. I'll just come to the slide to elaborate that answer. So basically, now this hydrogen is kind of novel, but it's not completely novel. That's the nicety of this topic because if you can see this is the hydrogen energy application I would characterize as we have industrial integration for like steel, electric generation for power generation. We have vehicles, we have import industry, we have building heating, resource recovery, a lot of industries. But the major use of hydrogen goes back to 1950s because this has been explored as a space fuel by NASA, USA, like more than 60, 70 years ago. So most of the properties of hydrogen and their characteristics have been identified back then in 1940s, 50s already. But this did not come forth because on that time, this sustainability or green concept, our net zero emission was not a huge thing. So it just dialed down or went back. But since the 2000s or 2010, then the world was more urged to go find a solution for this global emissions or global warming. That's where hydrogen again re-emerged. So hydrogen is not new, but in the same time, the momentum has gained within, I would say, last 2 decades, more like after 2010, I would say. So since it's kind of novel, what the countries have done is they have identified the requirement of national initiatives. So they have produce national policies, strategies, roadmaps, vision statements, guidelines, different narratives, different around the world. So altogether, we have 65 countries that have published some initiative altogether. So you can see Sri Lanka is one as well. We have our own roadmap back in 2023 September. So basically, these countries are trying to come up with their own objective or own narrative towards where hydrogen would take them. So that is really interesting. So what happens is, if you can see these parts, this Europe part, so obviously we need green hydrogen, but they don't have the right renewable capacity to generate hydrogen because it's pretty less for them. So what they are trying to come up with is trying to find import means of hydrogen. So that what they are trying to do is they are establishing trade partnerships with countries like Australia, United Arab Emirates, Saudi Arabia, Chile, Morocco, USA, because they have high renewable energy capacity. So what they have done is they have established trade partnerships and they have set forth specific cost values for a hydrogen in the next 2030 or 2050. So that is like 1 kilogram per $1 for 1 kilogram in USD, 1.5 kilo US AUD for a kilogram for Australia. Likewise, different initiatives has identified different cost values and what they are willing to do for that as well. So this is so each country their own narrative is completely different. So as again, for example, by 2030, the Australia want to be the largest exporter of hydrogen, green hydrogen to the world. And in the same time, the USA and China want to be kind of like self-sufficient with hydrogen while giving some export as well. And the countries like Japan, South Korea, they want to import hydrogen in very large scales. And they have the, I would say, the most advanced technical capacity regarding hydrogen at the same time. So different countries has different narratives. So based on that, I can show this slide. So basically, this is again a figure from our research we have done identifying the global hydrogen supply chain. So we can see how these different nations have established trade partnerships all around the world. So if you take this figure, for example, you can see Germany, they are trying to bring in hydrogen to their country with these countries. Like you can see Australia, New Zealand, Chile, Nigeria, Morocco, Saudi Arabia, Canada, they're trying to bring in green hydrogen. And if you take the case of Australia here, you can see they are trying to give out hydrogen. So let's say Germany, South Korea, Japan, you can see it's the kind of give out. So I really like this figure because it showcases where we are at right now. So where the countries have focused to get their hydrogen demand, because the IEA, International Energy Agency, had predicted that the hydrogen demand would be 550 million metric tons by 2050. So this is how it will be catered. So this is really nice. So this chart will be growing again and again a lot for the next decade. So we have to see who will be taking the most advantage. So I really like to explain and emphasize this region. You can see most of these trade flows are going through this region. So this is why this topic is really important, because this is where we can capitalize as well. And we can talk about these next questions, I think, Samita, yeah.
Yeah, more interesting points come in this our discussion. So let's dig deeper. So as we know, Sri Lanka's power sector still relies on imported fossil fuels. So making energy, it makes the energy security a big concern. So could hydrogen serve as a viable energy storage and balancing solutions for Sri Lanka's energy mix?
Yeah, I think yes. To be honest, so these are again another manuscript and research we presented at the International Conference of Sustainable Built Environment last year. This was headed by Dr. Shanaka and Engineer Tari from LECO. I need to acknowledge them. So what we try to do is we try to identify what is the energy potential and what is the values that is currently available in the country. So these figures might be a little bit different from the accurate, because I took this from the Public Utilities Commission report 2024. So there could be some discrepancies, but basically, I think we have like hydro percentage around 40% in the country, but in the same time, we are using coal and thermal oil around 40% in the same time as well. But compared to any other country, I think we have almost already have renewable potential. I mean, we are already using almost 50% of renewable in our energy grid already, which is really rare. If you consider any other country, even Australia, that is completely different. So if you can have a renewable energy supply of 50% already, that means you are in a really good level in considering your energy grid. But the problem we are having right now, I think, Samir, you can add this as well. Maybe you are more familiar with this than me even. But the problem we have is we don't have the right base load, right? Because we are basically getting our base load from North Chole and Karavalapiti Lakpuji, right? If I'm not mistaken. Right, yeah. So I didn't hear you, Hamid.
Yes, you are correct.
Yeah, right. So basically, that is where our energy grid is a bit dirty, right? So, and if we want to make sure our base load is more consistent, what we need to do is we need to find a more reliable energy source that can produce energy in a steadfast way. And we have a good renewable solar input as well, but again, the intermittency should come. So even if you put more and more solar panels again and again and again, what happens is it becomes destabilized, right? Because it cannot handle that much of input in the same time, because it's just in the grid. So it's really technical, but in the same time that happens. So usually in Australia, our energy grid is really, the capacity is very much higher than the demand because of this renewable integration. So again, here also in Perth, in last month or so, the grid destabilized and there was power cuts for like 1 hour, 2 hours around the Perth area, Western Australia, because we couldn't stabilize the grid here as well. So this is the question. So we have this potential. So the problem is because Sri Lanka, it's the World Bank study shows that we have a solar irradiation of 4.5 to 6 watt per square meters per day. and capacity factor all around the year is around 18%, 22%. That means it's really high. So if we can make use of this, then what we can do is we can use this extra energy that is available in the daytime to produce hydrogen, and we can store it. And if we can store it during the night time, we can burn it, or we can co-fire with it, either coal or LNG or anything like that. And we can make sure our grid is stabilized. This is really important because this World Bank study showcased that the total renewable energy potential theoretically is more than 42.4 gigawatts. And the practical is now realized at 14.2, I think, at the moment. But we are having around 3.54 at the moment, and 2030 target is around 8.2. But our potential is really, really high, very much higher than these numbers. So we need to realize it. So the problem is that everyone is trying to say is that even we put renewable into the grid, our grid going to be destabilized and we can't use of this power. So why should not be using that power? We can use that power and produce hydrogen, obviously, and we just have to store it. And if we can store it and use it, our grid is much more steadfast and stable. And we can drive our different industries, operations in the country. And in the same time, if even our potential grows again and again and again, we can store it and we can sell it to other countries. So that is the most important part. If you can remember this chart, so we need to be placed in this map. We should be a producer or provider to, let's say, if India can be a provider to other countries because our potential is much higher than compared to India. So if India can be a potential provider, why can't us? That's the right question. So we need to capitalize this, I would say, this because this is really important because right now the whole world is trying to figure out a way. So if we can take the charge in the same time rather than being delayed, then we can make best use of it as well. So we have our own advantage, and at the same time we can provide to the world and find a extra income as well. Why not?
With the points you mentioned, so I think that the grid stability issue is not concern for Sri Lanka, and it already has become a question for other developed countries, isn't it? So
yeah, very much like Australia, USA, and many much. Yes, true.
Yeah. So then, as you know that we have renewable energy targets in Sri Lanka, and the missing point that you showed that in that graph, Sri Lanka was not there in that graph. So I think that we have some opportunities here in Sri Lanka for hydrogen, as you mentioned. So what are the most critical challenges Sri Lanka must overcome to develop a viable hydrogen economy?
Yeah, that's the right question, right? The very nice question. So basically, we have put the first step forth actually that we need to commend ourselves because we have this. I'm not sure whether many people are familiar with this document. This is a Sri Lankan National Hydrogen Roadmap that was produced by the PDSL, and it went out last year September, and this is already. This is already here. So we have kind of like a blueprint that is like preliminary level, primary level, but at the same time, it's a blueprint that we have been here. So we are the 59th country in the world to come up with something like this. So there's only 865 and we were 59th. So that means something. We have put our foot into the mix. So the crucial concerns what we have right now is, like I said, so this position in this trade position is really crucial. So the problem we have right now is we don't have a demonstrable capacity at the moment. That's the problem. So let's say every other country. So if I go back to this figure, so because Australia wanted to become a large exporter of hydrogen, what they did back in 2018 to 2021, so they came up with an agreement with Japan and they developed this ship. This was having a storage of 1,250 cubic meters. So this is called Susio Frontier. This is from John Hastings Port in Melbourne and to Kobe Port in Japan. What they did was they made use of this trade line and they shipped liquid hydrogen from here to here, showcasing it's possible. So this is what drives or attracts investment. So currently the problem Sri Lanka is having for enabling this solution is the problem we do not have the demonstrational capacity or the practical capacity. So in order to do that, what the best place to start, in my opinion, would be trying to figure out how much of, like, we need to do a techno-economic feasibility first. The roadmap is a good one, but it does not contain a techno-economic feasibility at the moment. So that's where we need to start. We need to realize how much of renewable energy that we put into the grid can be used to generate hydrogen. And then we need to realize what sort of hydrogen we're going to use. So either we can use liquid hydrogen, that's the pure form, or either we can like generate or produce methanol or ammonia or any other toluene or like liquid organic hydrogen carriers. These are things I'm talking about. So metal hydrides is not ideal for large scale storages. So either we have to go from this side, gas storages or liquid storages, or need to realize we are going to use ammonia, methanol, or toluene or any of these liquid organic hydrogen compound as our storage. What is the main criteria that you're going to produce? And then what are we going to use it for? So are we going to use it for any other industry or just for the power generation? Or are we going to have a hydrogen vehicle fleet? Because hydrogen vehicles are very popular around the world at the moment, because I think there are all together we have more like 100,000 vehicles already, and China alone trying to make this fleet up to 3 million by 2030. So we have Toyota Mirai, that is, this is the figure of Toyota Mirai. So it can drive up to like 600 kilometers per charge, and it only takes 2-3 minutes to charge a vehicle. So are we going to go in this narrative? Are we going to make use of these vehicles? Or otherwise, are we going to use hydrogen itself to power plants? Because right now, this is the Hillaby power plant in USA. They are using natural gas and hydrogen blend, a mixture all together, and put it into these furnaces or the turbines. So are we going to use this? Or are we going to use this to generate for industrial, or maybe like steel, refining, mining, chemical production, or anything like that? Are we going to use it for that? We need to be particularly clear about what we're going to do. And then we need to realize, are we going to import and export? Do we have the right capability? So we need to have right numbers. And once we have right numbers, then we can attract some, let's say, investments and interest from other countries like this. For example, Japan has announced 53.5 billion US dollars for hydrogen advancement within their country and around the world. So we can attract this funding. It is already there. What we need to do is we have to have right foundation, and we need to have the right demonstration capacity. And if we are ready to show this, obviously we can generate funding and we can attract funding and we can make use of it. We need to start. So the first thing I would say, Samita, the technical economic feasibility should be there, and we need to be pretty particularly clear what we're going to do in the next decade. We have to be pretty clear because we can't grab everything at the beginning. So for example, Australia is not keen on producing hydrogen, having hydrogen vehicles, but they are very keen about exporting. And like USA, again, they are not very keen about a hydrogen fleet, but again, they are more keen about like the power plants, the energy generation, and exporting. And South Korea and Japan, they're completely changing their whole vehicle fleet into hydrogen in the same time. And they are shutting down their nuclear power plants, and they want hydrogen for everything. Likewise, we need to be very clear about as well. For again, China, they are shutting down all of their traditional steel plants, and they're trying to come up with green hydrogen, the hydrogen direct reduction of iron methods to generate hydrogen, produce iron. So likewise, we need to be pretty clear as well. So that is where we need to be very concerned regarding hydrogen for Sri Lanka as a start.
Well, I think this topic becomes something we need to talk. Something it isn't need to talk like this. So I think it's something bigger than this. So I think this hydrogen economy thing needs some collaboration between multiple stakeholders, such as government, industry, and academia. So how do you see these sectors working together to accelerate hydrogen adoption, specifically to Sri Lanka?
Yeah, that's again a really good question, because this again, hydrogen is kind of novel, right? And again, another factor I haven't been forthcoming is the safety, because compared to gasoline or anything like else, the hydrogen has a really large amount of energy per kilogram if you consider denser form. And if it combusts accidentally, the safety, I mean, the combustion would be like really, it's like a bomb, to be honest. So it's kind of concerning the use of hydrogen. That is the main predicament we had using hydrogen as well. So what happens is in the same time, let's say you are storing it in a typical metal material. So what happens is this hydrogen molecule is really, really small. So what happens, it goes to the molecule structure of the steel or any other plate that you're using. So once it happens, if you have connections, let's say you are building a tank, and if you will be obviously having belts and nuts and bolts and likewise, this hydrogen molecule goes through it. And once it goes through and stays there, what happens is it weakens the element, the structural element. So then what happens is it becomes brittle. We call it embrittlement at the same time. And that means like you can, it does not have any elastic capability once this temperature and this embrittlement happens. So this is a particular concern. And in the same time, we need to find out what are the materials that is ideal to store hydrogen or transport it in pipelines, ships, and likewise. So this knowledge is still not there. So this knowledge needs to come from universities, research institutes, and likewise. So that is why this concern is really crucial. And in the same time, a government alone cannot drive this kind of initiative. There should be private partnerships as well. For example, if you say, if every industry around the world right now, they have the major partners or major players privately, they have a keen interest in hydrogen deployment. For example, if you take the aviation industry, Airbus is, they are funding the Zero E demonstrator, that is again using hydrogen, liquid hydrogen as a fuel for aircrafts because it's really polluting the aircrafts, our atmosphere. And in the same time, we have companies around the Europe, they are trying to heat the buildings using hydrogen. Right now, they are using gas, LNG or methane or something likewise, then they are trying to replace it. And again, the power plant companies like Hillaby and likewise, they are trying to integrate hydrogen at the same time as well. The main vehicle producers like Toyota, Hyundai, Honda, and everyone is trying to bring hydrogen as like a hydrogen fuel cell energy vehicle or internal combustion vehicle. They are trying to bring it as well. So as you can see, this is kind of like a map of stakeholders altogether. So everyone need to contribute, right? So the private sector is there, the government sector is there, and then the research institutes are there. Again, another important thing is the workforce, because this workforce need to be hydrogen ready. It's new, we don't know about it. So let's say universities have to have explicit courses to teach how hydrogen works. So let's say hydrogen as a storage, that component need to come into the university curriculum even. So then whatever the workforce that we generate into the country would have that particular knowledge. So you can see it's a complete map. It's like stakeholders all around the place. There should be a one link connecting all these things. So that is why these hydrogen strategies, policy documents, they're really important because that is the missing link. If we have that, that connects everything. That all the stakeholders and everyone, that connects it at that moment. Because right now we have the roadmap. This is why I'm showing this. Roadmap is showcasing what we want to do next 10 years, next 15 years, next 20 years. But we are missing the link how this organization, let's say, for example, University of Moroto, University of Perak, the University of Ruhuna, how they are going to contribute to this shift. And let's say the government itself, what proportion they are going to contribute into this mix. In the same time, the vocational training institute in the country, how they are going to contribute. And let's say our organizations like CEB, LECO, how they are going to contribute. And whomever interested the private party, how can they come into the mix, right? So that's why it is complex, but that complex structure can be managed and make use of using this policy and strategy, and document or policy regulations. So that is really crucial concern. So that is our next step. That's what I was mentioning here as well. So these stakeholders you are correct, there are a lot of stakeholders, but we need to manage them, and it's possible because right now I would identify 5 major economies around the world that is doing this correctly. That is again a result from my analysis. That is China, USA, South Korea, Japan, and Germany. They are doing it right now in a proper scale. And Europe altogether, driven by European Union, they are doing it again. So this is kind of happening already. So we can learn from them as well. And we need to take the next step. So that's where this managing of stakeholders is really crucial as well.
Great. I think our listeners now have a good understanding about hydrogen and hydrogen storages, and where the world is now and where we are now. So I need the straightforward answer, Engineer Miller. So if Sri Lanka wants to become a player in the international hydrogen supply chain, what immediate steps should be taken?
Okay, so that I can answer from this particular diagram. So this is basically kind of like the breakdown we identified from our hydrogen roadmap that is published in last year. So basically, we are trying to achieve three deliverables: energy security, affordability, and access in energy. That means everyone will have access to energy, and energy sustainability through green hydrogen. So this is our current deliverables, current targets at the moment, right? So answering to your question, Samita, right now with the blueprint we have not made plans to become a global player in the hydrogen supply chain. So that's what I'm trying to emphasize here as well. We need to go beyond this one, because right now we are trying to be self-sufficient from this, right? It's good because that's where we need to start, but we need to look beyond that as well. And in the same time, by 2030, the country is trying to have 4,000 jobs in hydrogen sector alone and $1 billion USD of investments. So this is really crucial. And we are trying to have an export revenue of 500 million from hydrogen. So this is not catered like how we're gonna export them as hydrogen liquid or gaseous form, or like for like an organic carrier or a chemical hydride, and whom are we gonna provide them to, which countries, where, which companies. So this is the things that we need to find out. And 10 billion US dollars for financial investment decisions. That means that we'll be securing 10 billion US dollars by USD billions dollars by 2030 to drive hydrogen in the country. So good targets. The thing is, we need to have proper plans for this. So that's the crucial concern. So in order to achieve these targets, there are like 7 initiatives that the country has proposed. Production, storage, transport is obviously covered, like I saw. Policy regulations have been shown. It's good. Research development, workforce development, and partnership development. So we have touched the right narrative, right points, but not in the right detail, I would say. For example, I can explain this. So what we did was, this is again kind of like a comparison with the leading hydrogen economies with Sri Lanka and other countries. So you can see the first one is against Australia and Sri Lanka, USA and Sri Lanka, Japan and Sri Lanka. So for production, storage, and ecosystem. So this scoring system, basically the performance scale. So the idea, so why this scoring comes, if I take, for example, what happens, let's say the production method, production cost, comparing the Sri Lankan hydrogen. So we are trying to make use of renewables using solar and wind. So for example, now hydrogen, what for Australia, what they're trying to say is they are gonna generate 0.5 million tons of hydrogen with electrolyzer capacity of 500 megawatts. That's their target. But when coming to our strategy, it is not there. So that means that that specific number we have not given there. And if you take again the cost of hydrogen, now Australia trying to say that we are going to produce hydrogen at 2 Australian dollars per kilogram by 2030. Now we are saying we are going to export hydrogen, but we don't have cost figure. We don't have not realized it. That is where the techno-economic feasibility comes in, right? So these at concern we need to address. So again, the storage methods, if you can see here, we are considering about liquid storage and high pressure gaseous storage at the moment. So we have not identified the liquid storage. Is it liquid hydrogen or ammonia? That we need to find out. And high pressure gaseous storage, are we which scale, for what application, how are we going to export it? That is not realized as well. So I like to show this figure. So this is something again we proposed, considering the hydrogen strategy for Sri Lanka. So if we are using ammonia, we can use this. We can make use of this because it already has, ammonia already has its own capabilities and requirements. And while we are having this, we can ship them and we can store them and we can use them for electricity generation and transport, heat transfer, a lot of things. So this kind of blueprint should be there. So that is the missing link for us to become a global player, player in the global hydrogen supply chain. So this scoring is not it's not like condescending. I'm really appreciating like our country putting our step forward, because there are more than 120 countries which have not done this, but we can do more than that. That's what I'm saying. So we need to have right scale, right numbers, and we need to be pretty specific. And once we do that, we can go forth from there onwards. That's what I'm trying to say.
Thank you very much for your comprehensive answer for my question. So I think you have told us everything you need to tell today. So, and you have answered all of my questions. And I think our listeners got some good insight about hydrogen and the roadmap and relevant things. So, I think we have some questions from our listeners. Before I read out the questions, I would like to ask our listeners if anyone want to ask, speak and ask questions from Engineer Miller, please. This is time for you. So then,
Hello, Mr. Engineer Amila.
Yes.
Yeah, I have some
Hello.
questions.
Hi.
Yeah. Presently, Australia have been using this process to extract hydrogen. What
Yeah.
is the economical process? Do you know any process about this extraction process?
Yeah, that's really thank you very much. So basically, right now the hydrogen production in Australia, I would say the largest scale the Australia have put there for interest is that demonstration project in Hastings in Melbourne that wanted to export liquid hydrogen from Australia to Japan, showcase the demonstration. So basically, that was gray hydrogen. So gray and brown hydrogen because we used coal. And basing the same method reformation and regasification and pyrolysis, we made sure that we generate gaseous hydrogen and we bring those gaseous hydrogen to Port Hastings, and there was dedicated infrastructure there. And we pressurized it and cooled it down and made it liquid hydrogen, and then again filled into the ship itself, and then we exported it. So right now, that is the I would say the largest capacity I have realized in Australia. So problem with this demonstration project was they are not very keen about the economical figures or the loss or anything like that. So there's not much data available like how much a kilogram was cost for like this hydrogen. So I think it should have been in a high scale, but we cannot realize its exact value. But right now, considering Australian hydrogen strategy, so we have like a countrywide strategy, and at the same time we have strategies for different states as well, Victoria, New South Wales, and likewise. So in this scale, they are very much keen about the electrolyzer capacity. So there are a lot of researchers going on and developing the electrolyzer capacity, the efficiency. So 40% and likewise moving forward, they have been realized and they are trying to make use of it. So right now, this technology, what they're trying to do is they're trying to make sure a kilogram of hydrogen would be at $2 per kilogram at the moment by 2030, and that is the export value as well. So this would be like 1.5 1.5 USD or something like that, but it need to be less to compare to US dollars. But that is the cost figure right now they are targeting at. And I can't say exact number, but I can put forth right now the extraction cost is around per kilogram is 5 or 6 Australian dollars. I would say that would be a reasonable figure.
The process, how we extract H2 from what is the raw material you use it, like water, how they extract?
Okay, yeah, I got it. So, yeah, so basically right now the largest, like I said, again, we are using natural gas to stay methane reformation, that is methane. And in the same time, we use brown coal lignite. This is using pyrolysis. That is again, the technology is there. And of course, the very pure water for electrolysis. So that is the main goal, to be honest, at the moment. But Australia right now, they have the brown hydrogen, the lignite and coal, and at the same time natural gas, because Australia is very rich in LNG. They have a lot of LNG. So basically, they have that technology as well. And right now, the hydrogen production is derived from that. But 2030, like you said, the electrolysis, the pure water, and using electricity from green resources, that is the ultimate or the going forth.
Okay. Presently in Australia, they are not using this water as a raw material for the production.
Large scale, not in large scales, but they are trying to come up with very efficient electrolyzer capacities, and we have a lot of demonstration capabilities all around the country, the CSIRO, and likewise there are a lot of capacities. So the country is trying to integrate this into like large scale production. So there are a lot of projects going on around the world as well, and same time around the country as well. So basically, they are kind of like, I would say, developing the technology into the industrial scale, but it is not still operational in large scale, I would say. Yeah.
Okay. Presently, we are using, CO2, carbon dioxide, as a liquid form for many processes in the food industry.
Carbon capturing, or
Yeah, carbon dioxide, CO2, we are using as a liquid in high pressure is about 100 bar, 100 bar and minus, in the lower temperature. The same kind of process, we can't use it for the H2.
I'm pretty much, I'm not sure what is the I think I didn't get the question, but yeah. So if you're asking about liquefying the CO2 and storing it like for like energy storage, and whether we can use the same technology for hydrogen as well. Actually, that is where the hydrogen storage is coming from as well, because I would say the hydrogen liquid storage is learning from LNG itself, because LNG is stored at minus 196 Celsius, that is 111 Kelvin, and liquid hydrogen need to be stored at 20 Kelvin. So that is the gap that we are trying to fill. So yeah, that technology is kind of the same, I would say. But if you're talking about the high temperature storages, that is something that falls out of my expertise. So I really can't answer it that particular avenue.
Okay, thank you very much. Thank you very much. And one more question: this H2, how do we use in power generation in the turbine? How do we use it?
Yeah, very good, very important question. Thank you very much for that question. So let's say right now the most straightforward use is co-firing it. Co-firing it in the sense like we have LNG power plants around the world. So we are trying to mix the LNG mix into the turbine with hydrogen. So there have been different production plants that have been testing what is the ideal optimized mixture. So it is like, could be from 10% to 40%. So there is, I remember 38% efficiency has been achieved in Hillaby. So that means that you can replace 40% of LNG with hydrogen itself. So that means the overall emission goes down. So this technology is getting developed and it is industrially available in the same time as well. So it's mixing them together and firing to the turbine. But in the same time, there's two projects I need to mention in France, the Siemens Energy, and in Germany. So what they have done is they have realized this 100% hydrogen operational turbine. So they have tested and they have proven it works. So there are some projects that's going on to make use these turbines in power generation as well. So that is realized, and now this technology is evolved into the industrial scale.
Yeah, this hydrogen we mix with the steam turbine or gas turbine?
Depends on the technology that they want to use, but basically steam turbine, yes.
Okay, thank you very much. Thank you very much.
Thank you.
Doctor. Thank you very much.
Thank you, Mr. Raviraj, for your valuable questions. Anyone have some other questions? Okay. If there are no any other questions, I will read out the questions, Engineer Miller. So,
Yeah,
Mr.
sure.
Damitha Veera Peruma has asked, what about the potential for Sri Lanka? I think Engineer Miller has already answered that question. Mr. Damitha, do you want further clarification? Okay, I think it is clear. So I will move to the next question. Engineer Lasantha Prasad has asked, Do you have any insights about efficiency of transforming hydrogen and use? Engineer.
Yeah, that's a really good question. I have to say, because think the problem with hydrogen is, I would say, so I would go back to this slide, this photo, I would say, because that is where this concern comes in. So if you consider, like I said, if you realize, or if you just compare the energy per kilogram between gasoline and hydrogen in liquid form, it is almost like 3 times. It's true, but in the same time, considering the required amount of electricity to generate it, let's say hydrogen, to generate hydrogen and to store it, even if you want to store it, then the cost of hydrogen goes a little bit, not little bit actually, like twice the cost of gasoline or petrol, usual petrol. So that's the problem. So if we just to use compressed storages, that means that we do not have to have a specific cooling down and making it liquid form, or just storing it like in pressure vessels, then the cost would be kind of like, okay, but again, the problem is this is not dense enough. So if you can see this, the compressed gas, it is like 7.8 kilograms per cubic meter. But if only we can use going to the liquid form, then we can achieve 70.9 kilograms per cubic meter. So if we are using this, if we want to go here, then the problem is we are using a lot of energy to generate this much of this hydrogen and to store it as well. So the common courtesy is, why we are trying to do this if it's more expensive? So that's the right question. So the problem is, again, we need to find an alternative to this global warming, because we cannot keep keep burning fossil fuels and all coal and everything. We need to find a solution. So again, another question now, so why don't we use ammonia or like methanol? And likewise, it's feasible, but we need to consider about the densities. So let's say if you have ammonia altogether, so ammonia density is around 120 kilograms per cubic meter. But the problem is it only has 17.8% hydrogen and rest is nitrogen. So that means that you have like a portion of hydrogen there. And if you burn nitrogen itself, it emits nitrogen dioxide. That's even more harmful than carbon dioxide. So you cannot use it again in the downstream. You cannot put it in an engine and burn it. You cannot put it in a turbine and burn it. That's not achieving the target we want. So what happens is in here, so this energy, so if we are using ammonia or something like that, we have to dehydrogenate it. That means that we need to remove this N2 compound and make it use H2 again. So that's another added cost. So justifying the cost is really difficult. That's true in hydrogen, but I think that is because this technology is kind of, because all other technologies like gasoline, fossil fuels, LNG, it is established. This is a new technology, so obviously the cost would be really high. But with technological advancements and going forth and carbon credits, tariffs, and all together, I think hydrogen could be competing with other kind of fuel by 2030 or 35, I would say. So efficient wise, I would say it's not really efficient at the moment, but we are getting there.
Okay, thank you for that comprehensive answer. Engineer Lasant, I think you are clear now. So there's another question from Mr. Chatura. Any organization, corporation actually implementing the hydrogen industry in Sri Lanka at the moment?
Can you repeat the question? Sorry, I didn't get it properly.
Any organization or corporation actually implementing the hydrogen industry in Sri Lanka at the moment?
That's actually a really good question. I'm not completely sure, but I think there were several discussions between the Atomic Energy Authority and the Public Utilities Commission and maybe CEB as well. But I'm not aware of any particular organization that have really keen interest at the moment right now. So, but I cannot comment on that specifically because I have no clear idea, because it's not published. And if it's there, I'm not sure though.
Then we have some other questions from Mr. Ravi Ras. I think those questions were answered. So then there is another question. Is the fuel cell technology economical in large scale for turn hydrogen back to electricity?
That question, I don't get the context of that question. So if that person is in the audience, can you like elaborate what you're trying to mean by convert it back to electricity? What do you mean?
There is another part of that question. What is the practice volume that has reached 100 bar or 200 bar?
Okay, so I think the best idea to elaborate this question in it would be taking example of the hydrogen fuel cell energy vehicle, because that is the most use of hydrogen fuel cell energy, this fuel cell. So what happens here is that we have cells of that is filled with hydrogen gas. So usually for cars we are using 700 bars, not 100 or 200 bars. We are using 700 bars, and in the same time for trucks and buses we are using 350 bars. So this is the level we are talking about. So this kind of a pressure that we are storing, like not much, even 5 to 6 kilogram of hydrogen within one car. And what we try to do is, everyone know how like when you put hydrogen and oxygen into the cell, and it becomes like a battery, and it generates electricity and it drives the motor. Same principle as a battery energy vehicle like a Tesla or anything like that, but instead of a lithium, cadmium or any other battery, what we have is a hydrogen battery. So if we can, like, if this process, again, it is ever evolving compared, same as the battery energy. So efficiency wise, it is, I would say, pretty much same to the conventional vehicle. But the thing is, we are not emitting anything, and we can take so it only takes around 2-3 minutes to recharge a simple vehicle of Toyota Mirai, and you have a 600-kilometer charge of this vehicle. So I would say this particular application, hydrogen fuel cell, it is at its most highest. I would say that is the most developed hydrogen technology around the world, even at the moment, because uh, South Korea and Japan, they have a lot of these PLD, which we call passenger vehicle duty vehicles, and China, they have a lot of buses and trucks, and USA, they have hydrogen operated mining equipment, and in Germany, they have trains hydrogen operated. And China, they are developing cranes now operating with hydrogen. So I would say this hydrogen fuel cell is they're at a very high level and in high efficient level as well. So if I come to specific effectivity values percentage wise, that depends. So as you can see, it's differentiate between the companies. So what they're trying to achieve, are they are trying to make more on performance, or trying to make more on the battery itself? So it varies, but the technology is really at a high level, I would say.
Thanks for that answer. So I think we don't have any other questions.
Do you have anyone that's want to raise a question from the audience? So
Yeah, please.
Hello,
oh,
can you hear me?
yeah.
we can hear.
Yeah. Okay, I have a question. Let's see about our transportation sector. Also, our hydrogen roadmap mentioned that our transportation sector going to convert to hydrogen in I think 2050. So as a few European countries do feasibility analysis of their country converting your vehicle fleet to hydrogen fuel cell vehicle. So as I know, there is no any feasibility analysis in Sri Lanka. If we are doing converting the fossil fuel vehicle to hydrogen vehicle, then we have to develop many infrastructures to store and transport the hydrogen. But then we have to consider about the cost of fuel hydrogen. So what is the best way to transport hydrogen as raw format or ammonia or different kind of hydrogen format?
Thank you very much, Shamila. That's a really good question, I would say, because right now I said in 2050 hydrogen demand would be 550 million metric tons according to the International Energy Agency, the IEA. Not even 1 or 2% of this demand caters for transportation, actually. So it comes in different narratives, industry and power generation, and likewise. And so the thing is, so the countries like Japan and South Korea, why they are promoting this fuel cell vehicles is that because they are trying to import hydrogen because they don't have the right renewable capacity, right? So what happens is, if you are using this hydrogen and if you convert them into back to electricity, and if you run a battery energy vehicle, let's say a Tesla or something like that, what happens is you are losing energy in the process because you are bringing hydrogen and you're converting it using a power plant or something like that, and you generate electricity in the grid. And again, if you're going to charge a vehicle from that, that means you're losing energy on the way. So that is why they are more keen on using hydrogen vehicles itself. So let's say they have a port, then they can have truck trailers or pipeline, they can come into a refueling station, and then they can refuel the vehicles and run from them. But in our case, that's different actually, because we have adequate renewable capacity. So we can make use of this capacity to run our grid, and we can use battery energy vehicles. What Chamila mentioned is really correct, because this refueling infrastructure is the most crucial part, I would say. Right now, even we have a lot of hydrogen vehicles around the world, the refueling station, these refuel stations like around, there is less than 1,000 all around the world. The maximum is in China, like 253 stations. And USA, they have like 30,000 hydrogen vehicles fleet, but the stations are pretty less, like 80 or something. And most of them are only in California. Everything else, you just have one station for like hundreds and thousands of kilometers. So basically, it's not efficient to develop this infrastructure again and again and do it. So that's why we need to be really keen about what is our target. So that's where this techno-economic feasibility should come, that as Tamila mentioned, because we need to realize, are we good to use hydrogen vehicles, or it would be better to run our power sector and use battery energy vehicles? So that's the crucial concern. Are we going to use it, or are we going to use hydrogen transportation? Because like he said, the required infrastructure, it's a really huge concern. That is something we have overlooked, I would even say. Yep.
Thank you.
Any other questions?
I saw something from Hashin. Oh, thanks, Hashin. Thanks, Hashin. Yeah, you've been really kind.
Complimentary. Thank you, Mr. Hashan.
I have another question.
Yeah,
Yeah.
please.
Is there actually, I was wondering about the practical limitation of the volume of hydrogen tanks when it is stored in 100 bar, 200 bar, or in liquid stage, because if we consider about the grid scale, that could be several hundreds of megawatts. So is there a practical limitation of the number of cubic meters or tons in a tank?
Yeah, true. Very true. That's the concern. So the compressed gas storage, just like you mentioned, if you are going to store it like 100 bar, 200 bar. So if you're going to use it in a tank like this, so if you have a tank that is up to 60 meters like this and have a diameter of 12.5 meters, 38 of these tanks would come into 5,000 cubic meter of liquid hydrogen. So 38 tanks, imagine like 60 meters long, 12.5 meters of diameter. So if you are trying to make use of this compressed gas storage, just like 100 bar, 200 bar to store hydrogen, that is not really feasible. So if we're going to do it, it need to be really huge. So that is why around the world, they are trying to store hydrogen underground in salt caverns and depleted natural gas reservoirs. So basically these reservoirs and these salt caverns, they has the capability to reduce these hydrogen like escaping from this volume space. So this technology, actually it is a lot of researchers have been carried out. I would say there are a lot of having in Melbourne as well at the moment. So they are trying to store hydrogen in this cap rock of the soil or the ground itself. So we are talking about million metric tons in this scale. So if we want to make it feasible in compressed gas storages, yes, we need to consider about million metric tons. So cubic meters even. So that's a really huge scale, million cubic meters. It's a really huge scale, like you correctly mentioned. So that's why in Melbourne, we are trying to use liquid hydrogen because it makes more sense, right? So right now, the hydrogen tank we have, I can show you actually. So this is the largest hydrogen tank in the world right now. This is in NASA in the, I can't remember exactly what is the platform, but basically this can store 4,700 cubic meters of storage. This is spherical. This is just around 5,000 cubic meters. So that's why we want to go to 200,000 cubic meters scale. So that is the LNG scale. So we have like many LNG terminals around the world. So we are trying to develop the technology to that scale. So that means that would be more effective, like liquid hydrogen. So, and if you consider any other method like ammonia, methanol, likewise, that industries are well established. We have 50,000, 60,000 tanks already around the world. But the problem is, again, the volumetric and gravimetric densities. So how much of hydrogen is available within ammonia, within methanol? Then again, the question comes, which is really effective or not? A lot of debates are going on, but you're pretty correct in mentioning that this gaseous, it will be huge if they're going to store it. Yep.
So I believe that all of our valuable listeners did not miss the chance to ask a question from Engineer Miller regarding this topic. So then I think that we have come to the end of today's episode. So first and foremost, a heartfelt thank for our esteemed resource person, Engineer Amila Premakumar, for sharing his invaluable insight on hydrogen energy. Your expertise has truly enriched our understanding of this emerging field. So I believe that it's
need to
all.
mention a small thing.
Yeah.
So I need to show our team because,
Yeah. Of course,
like I
you
said, this is
mentioned
like a group effect. It's not like just a single one doing everything. So this is a team effort. So our research team, the hydrogen team, is led by Dr. Shanaka and Professor Priyan and Dr. Sadeep. They are the lead in this team, and I have a lot of good four colleagues: Susiri, Upeka, Miller, and myself, and Hasala. All of us are doing this, trying to make this liquid hydrogen into like a good scale. So I really need to mention them because this is, like I said, it's a combined group effort. That's why we are trying to pioneer within ourselves. And in the same time, I need to acknowledge the university because they are allowing us to do this, and research team. And we are doing some cutting edge research as well. Like I said, we are trying to develop different materials that works at this minus 250 Celsius because like I discussed, it's embrittlement happens. And we are trying to come up with nice insulation that can hold at minus 250 Celsius. Really, really interesting stuff. So we have good instrument suppliers that is from USA. That works on this, and I need to mention them as well. And of course, Samita and Dushant, everyone, because you have been really, forthcoming in organizing this session. I need to really thank, because I would say this could be something that most of us is not much familiar within ourselves. So thank you very much for allowing me to talk on this topic. It's really important, and thank you very much for your key concern and enthusiasm making this program a reality. The team and everyone, thanks again. And of course, the audience, thanks again for delightful questions.
Thank you. I believe it's almost midnight there in Australia. So thank you again for your dedication in this situation. So then I also like to extend my sincere gratitude to Engineer Dushyante Vanyarajji, the chairman of ISL Young Member Section, for his guidance, and to ISL team for their effort in making this podcast series a success. So finally, a special thanks should go to our audience for their valuable participation and engagement, even on a weekend. So as we move forward, I hope today's conversation sparks further dialogue and action towards building sustainable hydrogen economy for Sri Lanka. So we look forward to meeting you in another exciting episode of this podcast series. So until we meet again, good night to all of you, and have a wonderful weekend. Thank you very much.
Thank you. Thank you very much.